Thank you, Billy, and thank you to the Energy Initiative for hosting this symposium. I am a Duke alum and a former Energy Initiative doctoral fellow, so it's great to be back here virtually. I'm now at Resources for the Future and happy to be presenting some work. This is early stage work with a great team of folks from RFF and beyond, Karen Palmer, Casey Richmond, who's formerly of RFF, and Vincent Gonzalez, and Derek Wiedelman, who is also formerly of RFF, is now a Ph.D. student at Maryland. And I'd like to offer a big thanks to the Sloan Foundation, not only for funding this, supporting this symposium, but also for supporting this research project as well. And then finally, I'd like to thank Pecan Street for providing data underlying this whole project. So this work is on counterfactual prediction methods using machine learning for the purposes of causal inference. And so in that sense, it sits kind of at the nexus of the machine learning literature as well as the economics causal inference literature. And the big question we're looking at is, can machine learning be used as a substitute for randomized controlled trials, or RCTs? And the context in which we're doing this is how consumers respond to time-varying electricity prices, as well as other different kinds of pilot projects that have been used to help reduce peak load for residential households. So when you have these kinds of projects that are meant to reduce peak energy demand, the standard way to evaluate them, the gold standard, is to use these randomized controlled trials, RCTs. So the idea, very simply, is you get a bunch of households, you allocate some randomly to a pricing state treatment, allocate others to a control group, look at how their consumption plays out over time after you implement the policy, compare the households, and you get a treatment effect. The problem with these is that while they are the gold standard, they can be time-consuming to run, they can be expensive, and sometimes they're just simply infeasible to do. And so they're great when you have them, but you don't always have a nice randomized experiment. So what we're asking is, can machine learning approaches applied to detailed smart meter data, which is increasingly becoming available, can that be a substitute for these gold standard RCTs? And so this builds on the recent work from Berlig and authors that are using these ML approaches to essentially generate counterfactual predictions. So we know how much you consumed given the treatment, and so can we use machine learning to essentially predict what we think you would have consumed without that treatment, and assign the difference between those two observations as the treatment effect. And so what we're doing is essentially this similar thing. We're saying, can do these counterfactual predictions, can they be used to actually replicate the results from RCT, but without actually having RCT, nice randomized data? And the implications of this are actually quite big for utilities and other researchers. If you don't have the resources to run an RCT, what is another approach that you can use with lower quality data and still get a good estimate? So in the context is time-varying electricity pricing. So why does it matter? I think a lot of folks in this audience might already appreciate it, but CAISO summarizes it pretty well, which is that a green grid requires flexible resources. So you probably are familiar with this duck curve on the left. So this curve, which represents the net load that needs to be met in California by non-renewable sources of generation over the course of the day. It looks vaguely like a duck, that's why it's called the duck curve. But as you can see, in the middle of the day, as more and more solar is being built out, that pushes down the belly of the duck. And we have plenty of generation at that point. But then around 5, 6 o'clock, when the sun goes down, and in normal times people are coming home and turning on their lights and their TVs and cooking dinner and whatnot, there's a big ramp up in demand at the same time as a big loss of solar generation. And so something needs to fill that gap. And the options, generally speaking, are gas, which is carbon intensive, so not ideal; storage, which is increasingly part of the story, but it's at the moment it's still niche; or responsive demand. And so this is a standard lesson from economics, which is that you want to increase the price of something when it's scarce, and you can decrease the price when it's abundant. But the idea is to send a price signal to consumers so that when the price goes up, when we have scarcity, that leads to changes in consumer behavior. So these projects have been piloted in a number of places and evaluated before. So there was one great experiment done by Pecan Street. If you're not familiar with Pecan Street, it's a organization in Austin, Texas that has highly detailed data down to the minute level of time step, sub-meter for individual households on individual circuits, as well as a lot of information about the characteristics of the households, as well as weather. And they ran this experiment where they took about 250 households and they randomly assigned some to be a control group and some would get these different treatments. So the first one is this pricing treatment, which is that between 4 and 7 p.m. on certain days, the price of electricity would go way up for these households, more than a factor of 5, with the intent of encouraging them to reduce their consumption. They also rolled out these other 3 different treatments. One is a simple web portal giving people information on their consumption. Another was to actually send people text messages saying it's going to be a peak day tomorrow, can you reduce your consumption? And then finally another group also got these specific recommendations, say reduce your air conditioning usage during these hours. So this program has already been evaluated using standard methods by Burkhart and others in a 2019 paper. And roughly speaking, what they found is that this pricing treatment did have a significant effect on peak energy use, 14% reduction, but these other appeals and web portals didn't really have an effect. So this is, again, your kind of gold standard RCT approach. So you can see the results here. This is very clear. You've got your treated households in red over the course of the day. The gray area is when those peak prices were in effect. Compare that to the pattern for the control group during the same period, and you see a big gap appear during that peak pricing window. And again, standard methods attribute that gap to the treatment effect. By contrast, you see no effect of the text message. So again, very standard RCT gold standard estimate to get a solid handle on what the treatment effects are. But the question you might be wondering is, if we didn't have an RCT, how would we evaluate this policy? If we didn't have that green line, how could we estimate the impact of this policy? And so that's where the ML approaches come in. Essentially, we can use ML based on your historical data to see what would that red curve look like absent the treatment. So essentially kind of generating that green curve through machine learning counterfactual prediction. And so here's just kind of a stylized graph. On the left-hand side, we have historical data. We use a flexible machine learning algorithm to fit that data. And on the right, after we impose the treatment, we project what your counterfactual prediction might have looked like out of sample and compare that to the observed, your data, what you actually consumed, and that delta is your treatment effect. So that's roughly speaking what we're doing. Big picture, we're training several different machine learning models of energy use using only pre-treatment data such as weather, so temperature, humidity, pressure, and so on. Household characteristics, things like do you have size of the house, do you have PV installed on your rooftop, that kind of thing, as well as flexible temporal patterns. This is still early stage, so far we've implemented this work using lasso and random forests, and we're still working on alternative approaches such as boosting or recurrent neural networks as next steps. We're happy to hear feedback or suggestions from folks during the Q&A or afterwards. But with each ML model, we predict what your counterfactual future energy consumption might have looked like to generate the prediction error, the difference between your observed consumption and what we predict you might have consumed if not for the treatment. And then we estimate the treatment effect using a standard diff and diff approach on the prediction error. And then we're going to show it two different ways. One is with a control group, either this experimental control group from the original RCT or a new control group of similar households from a similar neighborhood that we reached out and found. And then we do it separately without any control group at all. So this is with purely observational data. Can we replicate the ground truth gold standard estimate of the treatment effect? So there we go. So here's the main results from just the pricing treatment. So the bottom left bar here is our ground truth. That's using the data from the RCT. We have our treatment group and our control group. That's the solid estimate of what the treatment effect should be. That's the bottom left. All the other dots do not use any information about a control group at all. So the naive comparison, the next one in gray, is just looking essentially a before and after comparison among the treatment households, changes in energy consumption. And you get wildly the wrong answer with using again, just the treatment households, standard methods, no ML. However, if we generate a household by hour specific counterfactual prediction, essentially a pseudo control group for each household and an hour, if we generate that and we use that and run essentially a diff and diff on that prediction error, then we get the results in the bottom right, three bars, showing that we replicate the ground truth RCT treatment effect using only non-experimental data, only treated households. So this is great. This is not restricted to the pricing treatment either. Here's an example from the text message treatment, which, as I said, didn't have any effect in our ground truth data. The naive approach estimates something that's huge and significant and of the quote unquote wrong sign. Compare that to the lasso and random forest approaches. Again, we're accurately replicating a null result when there is a null result. So just to summarize, the machine learning counterfactual prediction methods are replicating the result from experiment with non-experimental data, which is great. However, so this is what we get when we only use the treatment group. If we throw in our control group, so we actually have our real randomized control group here, then we're also replicating the treatment effect, which is great, but it also isn't really helping us either. So basically the idea here is that these approaches are generating a pseudo control group that doesn't really buy you anything if you already have a reasonable control group. So the same thing is true for pricing, and it's also true for the text message group. So bottom line, again, they still work here, but you don't necessarily need them when you actually already have a good control group. So just big takeaways. So counterfactual prediction with machine learning can replicate these experimental results with non-experimental data, which is great. However, if you already have a control group, you already have an RCT, then it doesn't buy you much, which makes perfect sense because they're using the same information. But this is big. This can be really useful for utilities and other researchers who may not have the resources to run RCTs, but still want to evaluate the effectiveness of these policies. As I said, this is still early stage work, so we are open. We'd love to hear feedback from folks about other ML approaches that could be useful in this context to explore. Thanks.
I was fascinated by this presentation, Brian. I mean, just to be clear, you still have to do the treatment. Like you have to, change the price or something. What you're saying is you don't need the control anymore. You don't have to do the randomized control. You basically just have to do the treatment, right?
Yeah, that's right. So the issue with the RCTs is that you actually need to collect households and randomize them into a treatment and a control group here. What this is saying is that you don't need to do any of that randomization. You just roll out the policy and then you can.
Yeah. So I guess a question I had was, so kind of what you're saying is I can get the answer about the policy effect without randomizing, but I was wondering, could you do more? Is there a way that you could think about a treatment to roll out that would not only you could evaluate whether it had the effect, but it would actually give you even more information about how to fine-tune the policy? Like, have you thought about whether or not you could imagine rolling out a couple of policy changes, not randomized necessarily, but just kind of conveniently done to different groups, and then get information about maybe optimizing the peak pricing or some other variable that you could fine-tune? Has there been any experiment with that or thinking about that?
So yeah, I think the answer is yes. Two responses. So one is certainly you could roll out different kinds of pricing policies to group A and group B, and just run this separately for each of them and compare how big the effects are. And I don't think that's necessarily tuning the model, it's tuning the policy, right? So you say the policy that raised the price more had a bigger effect by this much. Is it worth it or is it not? That kind of thing. Separately, these and related methods can be used to actually also get at heterogeneous treatment effects. So one of the chapters of my dissertation was focused on heterogeneous treatment effects using machine learning approaches. And those can be used to better target policies towards households that might be more or less responsive to them.
Okay, great. I will move the Q&A window is getting populated, so I will turn to some of those questions now. At the top is a question about whether or not you can generalize to other situations and contexts. So once you have this estimated treatment effect in the jurisdiction or data set that you have, could you extrapolate to, or maybe interpolate to other regions, other houses, things like that?
I think in principle you can apply the same model. You probably would want to retrain it in your new situation. You know, the model that predicts electricity consumption well for Austin, Texas might not predict electricity consumption well for Maine. And so you probably would want to re-estimate it using data from Maine, say. But you would need, you would need that data to generate predictions anyway. And then separately, you need to make sure that the things that you're throwing into the model are things that are relevant predictors. So heating degree days might be more important in the north versus the south, for example. And so just you need to make sure that you're including the universe of useful information when you do that.
Got it. One question is, does the method give information about causality?
Yes, yeah. So that is actually the main thing that we're trying to get at. Yeah, again, the point of this work is it sits at the nexus of machine learning and causal inference, and it's contributing to that that literature that is a large and growing literature of ML4 for causal effects. And yes, and that's exactly the point, is that we're generating a pseudo control group, and when you have a good control group, whether it's a real control group or one generated through these ML predictive methods, then you can establish causal effects.
Great. Another person asks, do you know anything about what the consumers are doing, or do you just know that their energy is less?
Yeah, so that's one of the great things about the Constreet data is actually they have information at the, that's not just at the main meter level at the house, but they actually have individual circuits monitored. And this is not a contribution of our paper, it is a contribution of the Burkhart et al. Paper that is looking at the same experiment. And they basically did the same thing for total consumption and for AC specifically, the energy consumed by the AC, as well as everything else, everything non-AC. And they found that basically all of the reductions from this pricing came from AC, adjusting AC.
I would have thought that. Somebody's asking, I guess this is kind of the question I started with, but how would you describe the extra expense of the experiment versus just doing the treatment? I mean, you talked about it a little bit, but maybe repeat what you said or elaborate a little bit.
So I don't have the numbers on hand to tell you exactly how much running this experiment costs, but in different contexts. So, well, first of all, in this case, they had to establish these separate accounts for each household that was independent of their utilities account. So there was a non-trivial cost setting this up. In addition, this whole organization, Constreet, which is great, they provide us the data. This is kind of what they do full time, is these kinds of things. So it's certainly a non-trivial thing. And then in other contexts, you just can't always run an RCT. Either you don't have the staff, or companies may be reluctant to randomly assign different kinds of pricing structures to different customers. And so, even when they maybe can be done cost effectively, there might be other reasons for resistance to these kinds of randomization policies.
Everybody can join me, please, in thanking Brian for a really excellent presentation. It was cool to see the work that was going on there.